Thank you. Thanks for the invitation to speak, and it's really a pleasure to be here. So I think that the story starts with topological Morse functions. So when doing Morse theory, the standard theory assumes that your function is smooth. If all you want to do is compute homology, then it's enough to assume that the function is continuous and that the notion of there's a notion of non-regular point that is then non-degenerate. So a topological Morse function in this sense is sufficient to compute homology, but you lose some of the functionality of the usual Morse theory because topological Morse functions can't be deformed. So it's kind of long for me to write down a definition of topological Morse function. I can write it down if people want it. It just basically says that you have this notion of regular point and critical point. And near a critical point, then up to homeomorphism, you've got a particular type of parameterization from which you can define the index. That's hard to say. I mean, the topological Morse functions, it's not clear that they're dense in the same way as the smooth Morse functions. I don't know how to count them. Yes. Oh, well, what Morse did was to write it as a composition of a homeomorphism and a smooth Morse function. So in that sense, there's more topological Morse functions. But the homeomorphism might not be unique, and certainly you can't deform these things in quite the same way as smooth Morse functions. So, I mean, in particular, up to homeomorphism around a critical point, the level sets look the same as for a smooth Morse function. Okay, so take a hyperbolic surface of genus G. I'm going to call this SG. So my surfaces are just topological. Well, there's no marked points, there's no punctures. They're just honest surfaces with a hyperbolic metric, for the moment unmarked. And then a systole is a shortest geodesic. On the surface. So on every surface, you have at least one systole. Let me draw it a bit more clearly. So here is one systole here. In particular, systoles are simple curves, homotopically non-trivial. And you can show by a cut and paste argument that a pair of systoles can intersect pairwise at most once. Otherwise, you construct something shorter. Okay, so there are finitely many systoles on each surface. I'm going to say, this is my notation for the Teichmueller. Surfaces. And then I want to define the systole function. From Teichmueller space into the positive reals. So a point x is mapped to the length of the systoles at x. So the systole function f sys is piecewise smooth. This is because where the set, at places where the set of systoles changes, the one-sided limits of the derivative on both sides don't typically meet. So it's not smooth, but it is a topological Morse function. Okay, so what do we know about the critical points of the systole function? Well, we know where they're not. So we say that a set C of curves fills SG if, well, let's say GD6. I'll confuse curves with GD6 when convenient. It fills FSG if the complement in SG consists only of polygons. So this is another way of saying that any homotopically non-trivial curve on the surface intersects at least one of the curves in your set. So I believe that Bears is the first person to have proven this, but it features heavily in Thurston's work. He showed that if C is a set of curves on SG that do not fill, then giving SG a marking and thinking of it as a point in Teichmueller space then there is an open cone of directions in Teichmueller space in which all the curves in the set C are strictly increasing, in which the length Okay, so one way of finding such a direction is to consider a geodesic on the boundary of the subsurface filled by these curves. And then the Weil-Petersen gradient of the length of that curve gives one such direction. This is a consequence of Riera's theorem. So he has a formula that studies the inner product, the Weil-Petersen inner product of gradients of lengths of curves. So what this proposition says is that away from where the set of systoles fills, then the systole function has no critical points. But we know that the systole function must have critical points, because it's zero sort of as you go out to infinity of Teichmueller space. And Teichmueller space is a disk. So at the very least, it has to have one. In fact, it has to have more than one because it's actually a mapping class group equivariant function. So if we have one critical point, we have a whole orbit of critical points. Right, so where are these? So the Thurston spine is a set of all points in Teichmueller space at which the systoles fill. So we see from this proposition that the critical points of the systole function are all contained in the Thurston spine. I don't know why he calls it PG. I think maybe some kind of projection, something like that. So, right, what do I want to say about that? So PG has a structure, well, it is triangulatable. That's because, well, the strata making up PG are defined by a certain type of equalities and inequalities of analytic functions. So there's a theorem by a guy called Logiatsiewicz that says that any solution to this set of this type of system of equalities and inequalities must be triangulatable. So basically the Thurston spine is a CW complex contained in Teichmueller space. You can say a lot about that. This is something that's not well understood in the literature. Basically, there exists a sequence GI. I goes to infinity. So for very large genus, it's almost everything. I'm going to get into trouble from my collaborator by saying this because we haven't put this on the archive yet. But it comes from understanding the local structure around critical points. And I can explain this to you afterwards. Okay, so one example that I want to give of a critical point is the Balsa surface. So this is a surface. Its fundamental domain is an octagon. The corners all have angle I/4, and opposite edges are identified. So this has, if I remember rightly, 12 systoles. There's one like this, one like this. And I think there's some going like this as well. Etc. So the length of the automorphism group including the orientation reversing, has order 96. And Fcis takes the value to inverse cosh of 1 plus √2 at this point. So this is the most symmetric example of a surface in genus 2. And what we can say is that it must be a critical point of any mapping class group equivariant Morse function on Teichmueller space. That's because it's an isolated fixed point of the action of the mapping class group on Teichmueller space. So wait, put this one up. They're really quite stiff. There. So Thurston has he has a construction of a mapping class group equivariant deformation retraction of Teichmueller space onto the Thurston spine. That's why it's called the Thurston spine. So this construction essentially uses the proposition due to Beers to say that at any point not in the Thurston spine, you've got a direction at which all the shortest curves, in some sense, are increasing. So when you take that vector field, smooth it off, take a flow, he argues that that gives you a deformation retraction onto the Thurston spine. There's a lot more I could say about this, but I've been talking a lot about this particular construction lately. And so if anybody's interested, I can talk about the details afterwards. So his construction, although he didn't mention Morse theory at all, reminds me very much of a deformation retraction of a compact surface with, well, a compact manifold with boundary onto a Morse-Smale complex. So in Thurston's construction, there are a lot more technicalities, but the basic intuition is very simple, and it's something that we've seen before. Okay, so now I want to get to the work of Schmutz. So Schmutz was another guy who did a lot of pioneering work in this area. And in fact, he wrote a number of really beautiful papers and then just disappeared from academia. And so it's a bit mysterious what happened to him. To talk about the work of Schmutz, I need to define a length function. So given a geodesic, or given a curve, if we think of this now as the topological surface, you have a curve, homotopically non-trivial, and at each point of Teichmueller space, you have the length of this curve. So a length function and so I want these all to be strictly positive, and these guys are curves. You take a linear combination, A-I-L-C-I, and this is a length function. So it just generalizes the notion of the length of a curve. Okay, so important thing to know is that length functions are analytic and convex. Convex in many ways. So they're convex along Weil-Petersen geodesics. They're convex along earthquake paths. You can define certain Fenchel-Nielsen coordinates with respect to which they're convex. They're very convex. Okay. So maybe, no, a filling. Let me write this as C, the set of curves. Write this as LAC. Sorry? Yes, all curves are closed. A here. Then that has a unique minimum in Teichmueller space. Okay, so we see it's a necessary condition that C is filling, because otherwise this proposition says there's always a direction in which all of these, the lengths of all of these curves are decreasing. So Schmutz defined these sets of minima, which are a generalization of Kirchhoff's lines of minima. So, in C. Then and min C is the set of all points in Teichmueller space that can be realized as the minimum of LAC for some A. So I'm assuming that all the entries in A are strictly positive. Okay, in practice, what's a more useful definition is to understand a certain geometric condition under which a minimum occurs. And so choose any metric, such as the Weil-Petersen metric. Then you have the gradients of the lengths of the curves. Well, we can talk about this without gradients, actually. So it's the set of all points such that for any set of all points x in Teichmueller space, such that at x, any derivation in the tangent space at x, the Teichmueller space, has the property that either any derivation C so either the derivation evaluated on the length of each curve in your set C is 0, or there is a C1 belonging to C and a C2 belonging to the set such that the derivation 1 is greater than 0 and the other is less than 0. So what does that mean? It means the gradients look something like this. In any direction, at least one of them is increasing and at least one is decreasing, or you're looking at the orthogonal complement of the gradients. So this property is called, the French call it eutactic. So when you have this condition, you can always find a tuple, in this case in R3, of coefficients, so that when you take when you weight the lengths of the curves appropriately, the sum of the gradients adds up to 0. And because the length functions are convex, that's a necessary and sufficient condition to have a minimum at that point. So these sets of minima are very convenient for understanding the critical points of the systole function. So let me give you a very important example. They're convex. Strictly convex. So no. The coefficients are all positive. There's no negative thing. I mean, in this example, you take, this is gradient LC1, gradient LC2, and gradient LC3. Then there's a there's an A1, A2, and A3 such that is 0. And then A1 LC1 plus A2 LC2 plus A3 LC3 has a minimum, has its unique minimum at that point. That's right. Exactly, yes. So the gradients are not contained in a half space. And whenever you have this condition, you can find such a linear combination that gives you a length function whose minimum is realized. So for a set of filling curves, min C is not empty, is what Schmutz showed. So let's take, maybe I should do it in a different color. So here's a set C of filling curves. Right. So Schmutz said that obtain critical point in each genus index 2G minus 1. So this construction generalizes to any genus. These sets of systoles cut the surface into 2G plus 2 gons. And in each genus, it gives you a critical point of index 2G minus 1. So this index is important because it's the codimension of the virtual cohomological dimension of the mapping class group. So in each genus, you get such an example, and Schmutz says that min C is a differentiable cell of dimension 2G minus 1. And one can think of it sort of as being like the unstable manifold. of the critical point. So I've got unstable manifold in inverted commas because this is just a topological Morse function. So strictly speaking, the stable manifolds and unstable manifolds might not really be defined uniquely. In practice, that's not a problem because you can choose them to be mapping class group equivariant, and then they tend to be unique, as in this case. Okay, so that's an important set of minima, and it's important for the following reason. So Hara showed that Harvey's complex of curves has homotopy type of an infinite wedge of spheres of dimension 2g minus 2. Okay, and then so Ivanov, Hara showed that Harvey's complex of curves is mapping class group equivariantly homotopy equivalent to the boundary of the thick part of Teichmueller space. Yes, okay. Let me write this down and then I'll do that. Mapping class group equivariantly homotopy equiv to boundary of thick So Harvey's complex of curves how much more time do I have? Oh dear, okay. Better get a move on. It's a simplicial complex Our vertices correspond to simple curves. On the surface. And simplices correspond to multicurves. So you have a simplex with a simplex with vertices given by any multicurve. With So this is a simplicial object, and it's being used for studying the mapping class group and Teichmueller space and so on, because these kind of disjointness properties are used to describe metrics changing, I suppose. It encodes a lot of kind of geometric information in a coarse way. So you can think of this complex of curves as living on the boundary of the thick part, because where you've got the systole function equal to the Margulis constant, you know that the systoles are disjoint. So informally speaking, you take the set of disjoint systoles, and that gives you a point in the complex of curves. So you have an action of the mapping class group on the homology of the complex of curves, and that gives you the Steinberg module. So if you take the boundary of, you take this example, this unmarked example, then the set of all possible markings give you balls in Teichmueller space whose boundary corresponds to, and the set of all the boundaries of these objects correspond to the generators of the Steinberg module. How do I say this? Let's just say it like this. With all possible markings of the Steinberg module. Now, given that I've run out of time, and I haven't even defined Schmutz-Thurston duality, I want to compare the work of Schmutz and Thurston. So the basic intuition is that Thurston studied the stable manifolds of F cis, and Schmutz studied the unstable manifolds. So there's technicalities here and there's fine print, but that's the basic intuition. In a sense, they were looking at the same thing. I think I should end it there.